Hey, I'm Nick, and I'll be walking you through the third bearing calculations that I did for my Mechie 360 project, specifically around slopes and deflections, but you'll be able to use this for a couple of other things as well. Yeah, so the first thing you want to do is solve without the middle bearing, and I just want to be clear, this is a middle bearing. That's what all the equations are based off of. So RB is applied in the center of the shaft. So yeah, anyway, you get rid of that middle bearing and then you solve it. You probably already have this in your SMath if you're doing the project. So pretty simple. Yeah, so this is what it looks like in the SMath. We have, our reaction forces, and then this is something that I do. I developed this S1, which is a singularity function for the entire beam as a function of n. And so I can plug in whatever number I need to. If I'm looking for the moment, I might plug in a 1. If I'm looking for the deflection, obviously I'm going to plug in a 3 here. So that's something I do that I haven't seen a lot of. The other thing I do is I keep everything as a function of P, A, and X, and actually IO, which is just differentiating between the input shaft and the output shaft. So yeah, PA and X, where P is the force applied, so that'll be your radial or tangential force from your gear. A is the location of that gear, and then X is the place where we're trying to find the deflection or moment or whatever that is. So yeah, PA and X. And then we just solve for the first constant of integration. The second constant of integration is always going to be 0 because your deflections, your slope has to be 0 at L equals 0. So that's just that. So yeah, we have our singularity functions and our input and output there. Yeah, so next we kind of remove P, and then using this kind of free body diagram here, we calculate what the midpoint deflection is if only RB is applied. And this will make sense in a few slides when I show you the diagram, but it's this value here. Essentially, we rearrange that so that it's equal to this Y1 that we calculated earlier at the midpoint of the shaft, so L2. And then, yeah, once we have our B, we solve for Y2 exactly the same way as we solved for Y1. So it's just that. Yeah, and then we use superposition. That's a pretty simple concept. There's obviously deflection caused by P and a deflection caused by RB. And just as long as the deflection at the midpoint caused by P is the same as the deflection at the midpoint caused by RB, then we have this kind of superposition thing. And yeah. So that superposition actually carries over through everything here. So obviously we have the deflection, which is what we based it off of, Y1 plus Y2. But we also have shear flow like that, shear force, moment, and slope. And you can see again, everything's a function of PA and X. And then N for M is 1. For V is 0. For Q, it's -1. For theta, it's 2. And IO, again, if it's positive, I'm going to be looking at the input shaft. If it's negative, I'm looking at the output shaft. So that's pretty simple as well. And yeah, just one note is that the moment of inertia has to be constant for the whole shaft. Otherwise, the equations kind of break down and they don't really work together that well. So yeah, so what you want to do instead is just take the minimum moment of inertia, which is going to be using your bearing diameter. And I guess just, yeah, don't use a piecewise moment. Trust me, it doesn't work. So yeah, thanks for watching. Hopefully that was a helpful little rundown of that. Like I said, it is based on a central bearing on your shaft. If you can actually do it differently if you want to put your bearing somewhere else. You just have to calculate, instead of that RB L cubed over 48 EI. You're going to get a different value if you have, for whatever point, and you're also going to not evaluate at L over 2. Obviously, you'll evaluate it wherever you've put your bearing. But yeah, the principles are exactly the same for either scenario. I just did the calculations this way. So yeah, thanks for watching. Hopefully this helped.